Okay, so looking at a polyprotic base with a strong acid. So the polyprotic base means essentially that it can accept more than one hydrogen ion. So typically, we would be dealing with the conjugate bases of those polyprotic acids. So for example here, the carbonate ion, if you look at the charge, is a -2, so it has room for 2 hydrogens to essentially be added. So same thing again, you have 2 different equilibriums because you're going to have 2 different hydrogens being added. And then you would have your 2 equivalence points. So imagine if we were dealing with H3PO4, PO4. So if we were to look at the phosphate ion, right? So the phosphate ion has a charge of -3, so meaning it can add in 3. So you would actually have 3 of these equivalence points when you're looking at the graph. Okay, so in terms of titrations, really the only thing I'd like you to know are the difference between the 4 types that we looked at and how the curves are different from one another. So if you had to sketch a curve or interpret a curve, you should know what would be the types of solutions that are being used to do the titration. So buffered solution. So a buffer solution is really a weak acid or a weak base equilibrium. So it's something we've been dealing with already. So for example, acetic acid in water is a buffer solution. Ammonia with water is a buffer solution. Anytime you have a weak acid or weak base in water, that is a buffer. A buffer is just a term for an equilibrium system with a weak acid or weak base. So what a buffer is useful for is for maintaining the pH of a system. So usually you add a buffer if you want the pH to stay relatively the same. So how that works is essentially because it's in equilibrium, it will have shifts happening that will slow down the change in pH. So we'll look at the equilibriums and talk about how that happens. But first of all, how do we make a buffer? We essentially need to have a weak acid with its salt. So what I mean by that is we need an ionic compound that contains the conjugate base of that weak acid. So for example, let's say I was using HF as my weak acid. The conjugate base ion would be fluorine ions. So if I needed an ionic compound that has this, I could use, for example, sodium fluoride, right? So hydrofluoric acid would be my weak acid, and then fluorine ions coming from sodium fluoride could be my salt that I use. So essentially what you're trying to do is you have the equilibrium happening, but you don't want to wait around for it to actually reach equilibrium. So what you do is you add in some reactant and product at the same time. Now keep in mind, the salt that we use, you want to put, oh, that was not a great circling, but you want to put a metal ion that will not interfere with hydrolysis. So for example, I have to use something from group 1 or group number 2, because if I use something that is a conjugate of something that is weak, it's going to create its own equilibrium. We don't want many equilibriums to be happening. We just want to have the one that we are trying to create, right? The equilibrium of the buffer we want. So here we have an acetic acid titration. So that buffer region, if you remember I mentioned, was the time before it kind of swoops up into this equivalence point line. Every weak acid or weak base has its own buffer region. So meaning this is the point where you have toggling happening back and forth. Sorry, I'm laughing because my dog's on my lap and he's making me laugh. So you have the toggling going back and forth here in the equilibrium. Okay, so how do we make a buffer? So as I mentioned, the buffer can be made by taking amounts of the weak acid with a salt that contains the conjugate of that acid. So here we have an example. Here we have acetic acid. The conjugate of acetic acid is acetate. So notice the salt that we're using here is sodium acetate. Now it doesn't have to be sodium, it could be potassium acetate or magnesium acetate, but you want to make sure you're using an ion that does not interfere. So essentially, let's say we had this in a beaker. Imagine there's a beaker and we have water in there. If you were to just add acetic acid, you would reach equilibrium eventually. What we're trying to do here, when we make a buffer, it's typically because we need it for either a laboratory or a different system that we want to add it to. So we don't want to kind of wait around and wait for equilibrium to happen. We want to get this equilibrium going right away. So by adding in both the reactant and the product, what you're doing is you're essentially just speeding up the time that it's going to take for the rates to become equal, which is what equilibrium really is, right? The forward rate is equal to the reverse rate. So, that's essentially it. So we'll discuss this, but the same thing could be done with a weak base equilibrium. I'm just going to flip to this and then we'll go back and talk about how it resists pH. But a weak base equilibrium, you would do the same thing. So you would have your weak